The half-life of radioactive radium is 1,690 years. If the initial amount is 80 grams, how much will be left after 1,000 years? So we know this is a half-life problem, so it's going to be an exponential decay situation. So we can just begin with our general equation for any exponential decay, which, remember, if we're dealing with money, we call it our PERT formula, P-E raised to the R-T power. But since this is not a financial situation, instead of using P for principal, we'll use A sub 0. A equals A sub 0 E raised to the R times T power. So it'd be good to go ahead and define some variables right now. The quantities that are changing, of course, are time. Time is passing by. And then the amount of radium. So in this case, we'll say that T is going to be the number of years. And A, the amount of radium, is actually going to be a measurement in grams. So it'd be the number of grams of the radium, the radioactive radium. So you can start with the initial amount. This A sub 0, remember, is the amount of radium that we have at time 0. And it says right here that the initial amount is 80 grams. So you could go ahead and begin by substituting in your 80 for A sub 0, giving A is equal to 80 times E raised to the RT power. You could also begin by looking at this situation numerically in table form, and we know that at time 0 we have 80 grams. So now we need to move on to using the half-life that was given to us, 1,690 years. Now notice the units. This is a time. So we're saying in 1,690 years, this substance will decay to half of its original size. So if we began with 80 grams, then we'll end up with 40 grams in 1,690 years. So you can treat this piece of information as an ordered pair that we're going to substitute into our equation, and that's going to let us solve for R, which is our relative decay rate. And if you want to go ahead and substitute right this second, you can, or if you feel better rereading the problem and establishing what you're looking for, the question is how much will be left after 1,000 years? So that's a time. So ultimately, in the end, after 1,000 years, question mark, we're interested in how much we have left. So this table shows you all of the information given in the problem. All right, so now we can substitute. We know that we will end up with 40 grams of this radium after 1,690 years. So I'm substituting in the values that I have in the table into my model for A as well as T. And that gives us this exponential equation that we now need to solve. So we'll begin by dividing by 80, which will leave us with 1/2, or 0.5, is equal to E raised to the R times 1690 power. And then we'll rewrite this in log form, which would be log base E of 1/2. And if you want to go ahead and write natural log, of course, that's great, is equal to 1,690 R. So therefore, our value for R, we will input this in our calculator, will be the natural log of 1/2 divided by 1690. So as always, make sure you pause the video and check these calculations on your calculator so that you know how to input this correctly. So your calculator is going to return something like this, negative 4.1014 with some additional decimals here. And then you'll see a capital E followed by a -4. That's what the calculator is giving you. And this E business here, this is the calculator's way of writing scientific notation. So this is essentially the same as negative 4.1014 times 10 to the -4 power. So the calculator is returning the decimal to you, but in scientific notation, which of course this -4 as the exponent means we need to move our decimal 4 places to the left. So really the R value would be negative 0.00041. And that's not the exact value, that would be an estimate, an approximate value. And since we are going to use this value in our later computations, you'll want to go ahead and store this value using the store feature on your graphing calculator. So we have r is equal to negative 0.00041. Also good to note before we go further, notice that the r value is negative, and that's exactly what we will expect in an exponential decay situation. Since the amount of radium is decreasing exponentially, we expect to have a negative r value. That's our relative decay rate. So now that we have this value for r, we can substitute that back up here into our model, and now we have an equation. So the actual model for this situation would now be A is equal to 80, that initial amount, times E raised to the negative 0.00041 ... times T power. And again, just noting that we won't actually be entering this decimal, but rather this is going to be the stored value in our calculator. So now going back to your original table, what we were asking for here, we were looking for how much was left after 1,000 years. Therefore, we're going to just input 1,000. Written in function notation, that would just be A of 1,000. So now you'll input 1,000 in for T using your stored value for R, and then you should get an answer of approximately 53.08, and this was the amount of radium, which was measured in grams. So we would end up with 53.08 grams of radium after 1,000 years. And finally, before calling it quits, I always like to finish by asking myself, does this answer make sense at 53 grams? And we really are not going to know until we go back to our table. So let's go back to our table here. So we have an answer here of about 53 grams or so, 53.08. And does that answer make sense? Well, the half-life of 1,690 years, that was how long it took for the substance to decay down to 40 grams. So hopefully it does make sense to you then. In 1,000 years, you haven't decayed all the way down to half of the original amount. So this value of 53 makes sense because it's a value that's larger than 40, since we haven't made it all the way to 1,690 years. So in other words, yes, this answer does seem feasible, and we're done.